Hello guys, it's Emma, and this video is a brief introduction to limits of functions. Differently from university courses, we are not focusing on formal definitions, but we will try to understand how does a limit work. Consider this simple example. We have the function y equals x plus 2. Its graph is the green line you see in this picture, and we want to compute the limit of x plus 2 when x approaches 2. What does this actually mean? Well, we should simply look to what happens to the function x plus 2, that is represented by the points on the y-axis when x gets closer to 2. How can we answer to this question? Just think about walking along the graph closer to the point x equals 2, so this point here. What we have to notice is what happens to the function x plus 2 when we get closer to this point. You see that if I get closer to the point, say, coming from the left or coming from the right, the y points of the function get closer to y equals 4. Therefore, we say that the limit for x approaching 2 of the function x plus 2 is exactly 4. Let's see another example. Here, I drew the graph of the function y equals x squared, that is a parabola. We will now compute the limit of x squared for x approaching 1. How can we do that? Applying the same reasoning as before, we should look at the value of x squared when x goes to 1. To answer to this question, let's imagine to walk along the graph toward the point x equals 1, which is this point. You see that if I get closer to 1 either from the left or from the right, the y points of the graph tend to be 1. And therefore, we will say that the limit for x approaching 1 of the function x squared is exactly 1. Surely, some of you are now thinking, why don't we just substitute x with 1 in the equation? See that if 1 squared is equal 1, or in the example above, instead of doing all of those steps, it would be much easier substituting x with 2, do the computation 2 plus 2 equals 4, and seeing that the result is 4. Well, I agree with you with the idea that substituting in this case is perfectly fine, and may be convenient either, with respect to the above procedure. So, why should we apply such a complicated approach that seems to be rather confusing? The idea is that there are some functions that behave in sort of a weird way in proximity of certain points. For example, consider this function. X equals 3 is what we call a vertical asymptote. So, if we want to compute the limit of this function when x approaches 3, could we just substitute x with 3 in the equation like in the above examples? If you try, you see that minus 2 times 3 is minus 6. Minus 1 is minus 7, but the denominator is 3 minus 3, which equals 0. Of course we don't like it, because we don't know what is the answer, since division for 0 is problematic. Moreover, we could foresee the presence of a problem looking at the domain of the function. This function is not defined for x equals 3, because for x equals 3, the denominator is 0. Substituting 3 is therefore, let's say, not legit in this case. We can't do it, and then, to understand what is the limit of the function, we should literally look at what happens to the y points of the graph of the function when x gets closer to 3. As we're going to see in the next videos, we don't have to do this operation manually, so we don't have to look at the graph every time and see what happens when we get closer to the point under investigation. Fortunately, there are some shortcuts that allow us to predict the result of these operations without the above graphic procedure. This helps us save some useful time. In addition to the case of the vertical asymptote, there are other cases in which we can substitute x in the equation to compute the limit. Among these cases, we have the functions with a jump discontinuity, like the one you see in this picture. We'll analyze in depth all of these cases and the procedure to solve them in the next videos. Thanks for watching, and if you found the video useful, don't forget to leave a like and press the subscribe button.